All right, guys, what we're looking at here is number 1 from the 2021 first exam. It's a reading tables example. It's fairly straightforward. There's one part that I think threw a couple people off, but we'll get to that in just a second. So let's go ahead and dive in and take a look at what we got going here. Okay, we've got this table of values that says the density of bacteria population in a circular petri dish at distance r centimeters from the center of the dish is given by an increasing differential function where f of r is measured in milligrams per square centimeter. Values for f of r values of f of r for selected values of r are given in the table above. So pretty straightforward. It's just saying, okay, we've got a density. It doesn't change how we're going to do the problem, to be honest. It's a little bit different on the units. We'll get to that in a second. So letter A says use the data in the table to estimate f prime of 2.25, which is right here. Obviously, there is no 2.25. So we just choose the 2 points that are closest to that value that we're looking at, and we find the slope between those two values. When we put that in, you can leave your answer like that. If you want to simplify, it does simplify down to 8. And it's easiest right now to just put the units in. Now you'll notice 10 minus 6, that we got both of those values from here, so that is milligrams per square centimeter. Then we're, square centimeter, and then we divide that by centimeters, and really that's the easiest place to put the units so that you get the points there. Once you do that, it also wants you to interpret the meaning. Now remember, anytime you want to find the derivative, you just say that is the rate of change of whatever function we took the derivative of, so in this case f of r, when r equals 2.25. If you accidentally use t instead, that's fine. You'd still get all the points on that one. So there's your answer for letter A. You got everything that you needed to. Letter B says the total mass in milligrams of bacteria in the petri dish is given by the integral expression 2 pi times the integral from 0 to 4 of r times f of r. And it wants us to approximate that using a right-Riemann sum. Now where this differs, and this is the only place that I thought this problem was a little bit tricky, where this differs is we are doing a right-Riemann sum, but you'll notice the function we're looking at is not just f of r. It's r times f of r. So anytime we need to tell how tall our rectangle is going to be, I need to plug in both the r and the y value at that time. So my first rectangle is going to go from 0 to 1, so it's going to be 1 wide. And then it's going to be r, which I used that r right there. I plugged that r in, so it's a right Riemann sum. I use that r, and I multiply that by f of r. So 1 times 2 is 2. Plus, my next one is 1 times, this time it's going to be 2, because that's my r, times f of r, which is 6. That's going to be 12. And we continue on doing this 0.5 times, that's how far apart those are. Then I'm going to do 2.5 times 10, which is 25, plus 1.5 multiplied by 4 times 18, which is 72. And you could just leave your answer like this, and you could have left it way more multiplied out if you wanted to. Or if you simplify that down, you get 269 pi, which I don't have the decimal answer in front of me, but that's our approximation. The key here was understanding that my function is different than just the regular function that's being multiplied by the r that we're plugging in every single time, which changes how tall each of the rectangles are going to be. Letter C wants to know, is this approximation an over and underestimate? Well, if we're doing a right Riemann sum and it says that it's increasing the entire time, I've got an increasing function, a right Riemann sum. You can draw yourself a simple picture, although it won't get you points. But if you just say that you are increasing with a right Riemann sum, then what we can do is we can say, okay, since we're doing a right Riemann sum and it's increasing, that means this is going to be an overestimate. And that's all you have to put on letter C. Letter D says the density of the bacteria in the petri dish from 1 to 4 is modeled by this function. So now we actually have a function. For what value of k between 1 and 4 is g of k equal to the average value of g of r? Well, there's two parts to this problem. First of all, we have to find the average value of g of r. The way that we do that is we do the integral from 1 to 4 of g of r, and then we divide that by how long it took, which is 3. And when you put that into your calculator, you get 9.876. Now that we have that answer, it wants to know between 1 and 4, when is this function equal to that average value? In other words, when is g of k, which is just g of r, it's the same function, equal to 9.876? Well, we just graph both of those in our calculator, put that one in y1, put that one in y2, and we want to see where they cross from x equals 1 to x equals 4. And it just so happens that when the radius is 2.497, those two are going to cross. Again, I thought this was a fairly straightforward problem. There's a couple little tricks in there, but a fairly straightforward problem. Hopefully you understood that pretty well. If you have any questions, please let me know.